Okay, so the question is to count the number of ones in the binary representation of a number. For example, a number uh, 10 is given to us, and we have to find out how many ones are there in the binary representation of 10. So when you have to represent 10 in the binary format, then it's 1010 and the number of ones are 10. Similarly, if you have to represent, let's say the question given is 11 and the number given is 11, and we have to calculate how many ones are there. So method 1 is you can just convert 11 to binary, and that is 1011. So we know how to convert a decimal to binary representation, and so 1011, and you can count. You can just right shift and you can keep counting. So this is 3. Otherwise what you can do is you can uh, first take a number and you can AND it with 1. So for example, when you take 1011 and AND it with 1, you find out whether the last bit is 1 or not, and if it is 1, then you increment the value of count, and then you make n is equal to n right shift 1. So that time n becomes 101, and again you do the same thing. So you run the loop until while n greater than 0, and you do the same thing. But then what we're gonna do now is something different. In both of these you have to traverse each and every bit which is present in the binary representation. But there's another shortcut method which is actually a little difficult to think of. However, even when you know the solution, we struggle to find out the reason behind it. And that is, suppose you have n is equal to 10, and let the basically the logic is, while n greater than 0, answer is equal to 0. While n greater than 0, answer plus plus n is equal to n and n minus 1. Basically, the number of times this loop will run is equal to the number of ones present in the binary representation of the number. The number of times this loop will run is equal to the number of times the value of answer will be incremented by 1. That is in turn equal to the number of ones present in the binary representation of this number. But how is that? The answer lies in this particular statement. So each time you do the operation n is equal to n and n minus 1, the rightmost one will be eliminated. Again, the next time you do n is equal to n and n minus 1, the next rightmost one will be eliminated, and so on and so on. This operation will continue until all the ones are eliminated and we are left with n is equal to 0. But how do you know that each time you do n and n minus 1, the first rightmost one will be eliminated and then the next rightmost one will be eliminated? How do you know that? Let's take an example. If n is equal to 1011100, let's just take any random number. Now suppose you write n minus 1. Do you understand that the rightmost one available is this particular one, right? Now, in the binary representation of n minus 1, if n is this, in the binary representation of n minus 1, all the ones to the left side of this one, all the digits on the left side of this one will remain intact. And this particular one will become 0. And why is that so? Because the value of n minus 1 has to be lesser than n. Suppose I write this is also 1 and then I change these bits. Now these bits are all 0. Making this any of these 3 bits as 1 results in this particular number to have a greater value than this n, right? So therefore, I have to make the one at this position 0. And the remaining, and in the remaining, that is the ones to the right side of this one, the digits to the right side of this one will be changed. What will be changed? I don't know actually what it becomes, but then it could be anything. So that's actually 1011011. But whatever it is, we know that when we are ANDing it, since this is 0, since one digit present is 0, no matter what these digits are, always it is gonna be 0. Okay, no matter what you make, whether it could be 111, whether it could be 101, whatever it is, no matter what it is, this always becomes 0 because these digits are 0. Now, as I told you, the digit at this particular position also becomes 0 because the n minus 1 is lesser than n, and the digits on the left side of this rightmost one have to be remain intact. So 1011, and this particular one also becomes 0, and this is how the rightmost bit will be eliminated. Let's do this again. Now n becomes 1011 2 3 4. Okay, add an extra 0 here. Yeah, correct. 1011 0000. Okay, here I add an extra 0 anyways. Yeah. Now, what is n minus 1 in this case? Essentially, just look at the rightmost bit. All the digits onto the left side of this rightmost bit will remain intact in n minus 1, that is 101. This digit will become 0, and towards the left some Shedkhani will happen. Whatever happens, after ANDing it, since this is 0, it's gonna be 0, and this particular digit will become 0, and the ANDing of these will result in 101. Okay, so yeah, that's the logic. Whenever the logic lies in the binary representation of n minus 1. In the binary representation of n minus 1, the rightmost bit is taken, and the digits on the left side of this rightmost bit will remain intact because we want the value to be decremented just by 1. That is, the value has to become n minus 1. So therefore these digits will remain intact. That is how the binary representation of n minus 1 is. And this particular bit has to become 0 because we want the value of n minus 1 to be lesser. And here somewhere, some or the other, something becomes 0, something becomes 1, something happens like that in order to result in n minus 1. But whatever it is, the ANDing of these bits result in 0. The ANDing of this bit also results in 0. The ANDing of this bit remains as it is. So that's how each time you do n is equal to n and n minus 1, the rightmost one will be eliminated, and so on. This loop runs only until the number of ones are present. It runs as many times as the number of ones are present in the binary representation of n. Okay.